Good evening, everyone. Uh, I'm Hamid Bahai. I'm the Institute Director of Materials and Manufacturing, and I'm delighted to welcome you here today for this very special evening, the inaugural lecture of Professor Simon Shaw. Before I start, an important housekeeping note. We're obviously not expecting a fire, but should the fire alarm sound, please leave the building and assemble on the adjacent grass area. Our stewards will guide you. So these are the two doors, exit doors that you will need to use, but hopefully you won't have to. So I'm so pleased to be part of a series of inaugural lectures celebrating the careers of some of Brunel's most talented and creative individuals. I do hope you may be able to join more of these sessions from Brunel Research Festival this week. I'm delighted to be informed that our colleagues in the team are in the process of arranging some planning for an exciting autumn series of inaugural lectures. So hopefully you can join those as well. So being appointed as a professor is a special achievement, recognizing those who truly excel in their field. And I congratulate Simon on this well-deserved achievement. Simon is now a professor in the Department of Mathematics in the College of Engineering, Design, and Physical Sciences, and belongs to the Applied and Numerical Analysis Research Group. He is also a member of our Institute of Materials and Manufacturing and of the Center for Assessment of Structures and Materials under Extreme Conditions, and of the Center for Mathematical and Statistical Modeling. Simon, res- Simon, Simon's research interests include computational simulation methods for partial differential Volterra equations, and in these and related fields, he has published over 30 research papers. He is currently involved in an interdisciplinary project that is researching the potential for using computational mathematics and machine learning as a non invasive means of screening coronary artery disease. And I must add to that I've known myself, Simon, for a number of years now. I've had the pleasure of knowing him, and he has been one of the pillars of what used to be called BICOM, the Brunel's Institute of Mathematics, which was founded by John Whiteman sitting there. Um, I remember myself 25 years ago when I was considering whether I should join Brunel or not. One of the biggest attractions for me was indeed John Whiteman's institute, a well known, world renowned institute. And so I think we're not just celebrating the achievements of Simon, but also John's legacy at Brunel. Simon describes himself as an unlikely and unintended academic whose story doesn't fit the usual notion of a pre-talk bio. And I must say, just reading Simon's history, I find it very inspiring and really fascinating. Um, he left the school as soon as he could, didn't take A levels, and he ended up on a mech-eng, B-eng at Portsmouth um, on the strength of less than adequate apprenticeship qualifications because because the company he was working for went bust and his apprenticeship lapsed. After the first degree, he was a designer of dental X-ray processors, and these were the wet ones, long before the digital photographies that you have now. And then that company also went bust. He then realized, and I think that's the important bit, that while employment uh, could not be taken away, education couldn't. Sorry, whilst the employment could be taken away, education couldn't. And so he decided to return in CFD and structural mechanics with an MSc at Imperial. He wanted to work as an engineering consultancy, but instead got drawn into the world of finite elements and computational mathematics. He answered an ad for an CERC, which was the old name for EPSRC, a PhD studentships placed by John Whiteman at Brunel. He never intended to stay on afterwards, but he's still here. It has been too long, too good to walk away from, and I am sure Simon will be able to explain why in the next 45 minutes. I hope I have whetted your appetite for what promises to be a fascinating lecture this evening. And Simon, over to you.
Thank you, Hamid. Hello, everybody. Wow, I'm a bit touched. There's a lot of people here. I wasn't expecting that. Thanks for coming. I hope it's worth it. A lot of what I was going to tell you, Hamid's just said. So thanks for coming. I think there's some wine outside. No, I'm just kidding. Right, let's get rid of that picture. So it's a funny title, isn't it? I mean, from machine tools to machine learning via decay, dead poets, heart disease, and finite elements. So I'm going to try and explain that title to you as we go through. Just before we do, though, I'd like to say thanks to Hamid for asking me to do this, because he's organised the Structural Integrity Research Symposium today. So he's pretty much on his knees. He looks after that all day, and he asked me to do this in the evening. So thanks very much, Hamid. Thanks, Janet and Seb, for making it all possible. When Hamid asked me to do this, I said, "Are you sure you want a mathematician to do a public lecture? Because it's just, pages and pages and pages of equations." And he said, "No, I don't want you to do that." And the advice I got was try and make it personal, talk about the journey in some way. So I guess the journey sort of encapsulated in those three pictures. I'll tell you more about it. But when I first came here, I was in the John Crank building right at the top. That's gone now, and we moved into the annex in Tower A. And the John Crank building is now this lovely open space here. So this is the personal story then, and then we get to the real stuff. So I didn't like school. I found it boring. It wasn't that it was horrible or anything, but if you're a Pink Floyd fan, I relate to this quite a lot. The maths they taught, ironically, I just didn't like it. It was modern maths, not very applied, and for that age group, it just didn't feel right. So I left. I became a factory worker. I was offered an apprenticeship, and then I started doing all this stuff. I was talking to Hamid earlier on. I did this in night school and day release. Look, I'm doing calculus, the volumes of revolution. It was incredible, really eye-opening stuff. And it wasn't just the maths that switched me on at apprenticeship level. I was doing this stuff as well. So I made these things. I'm not putting them up there out of vanity. I'm putting them up there because I learned a lot from doing this. So they used to give us a rough piece of metal and an engineering drawing and say, make it. Some of these things, like those parallels there, had to be made parallel to within maybe half a thousandth of an inch. And if you didn't get it right, they threw it in the bin, gave you another rough piece of metal and said, go do it again. So I learned maths, attention to detail, and personal quality control and precision. And it stayed with me all my life. It's really helped me. So I didn't do any A levels, but what I did instead was this stuff, and it was, for me, much more valuable. So those were the tools of the trade, and those are the machine tools in the title, right? So that was how it began for me. But I got made redundant. The factory went bust, 6 months on the dole. Wasn't much fun. I worked for ICI, and I learned how to program one of these things. So this is a CNC lathe. They're all over the place these days, to a penny. But in the early 80s, there were hardly any of these. And I was this young kid, and they said, go and learn how to do that, because we don't know how to work it. So I learned programming. I learned programming on a lathe. And then I got one of these things. I've still got it. A programmable calculator. 38 steps. That's what you could program into this, 38 steps. I was into espionage novels at the time. I wish it had been 39 steps, but they missed that. And anybody, if you can see it, right at the top there, it says integral dx. It did calculus. In the early 80s, of course, it was definite integrals and it was Simpson's rule, but nevertheless, it did calculus. And I was doing maths, and then I had this idea of programming, and I could do maths with computers. And then the ICI job finished, and I moved to British Telecom, and I spent a lot of time at the top of these things. And if that looks like fun, then imagine. You haven't got any gloves on, you've got stripped wires, you're trying to make terminations at the top of a pole in January. The wind's blowing, the pole's swaying, it was snowing on one day, it was miserable. So I didn't really like that. And this idea of maths and computing kept coming back at me, and I managed to get hold of one of these things. And that was it, really. It just turned it all around. And I thought, okay, I need to do something. And I spoke to, well, he called me up, a man called Mr. Seth. He taught me maths in the night school that I was going to. So I was still doing that, even though the apprenticeship had lapsed, because I knew it was the only thing I had. And he called me up and he said, what are you doing? What are you going to do? And I said, I don't really know, because I couldn't get another apprenticeship. And these jobs weren't much fun. And he said, why don't you do a degree? And I said, because I'm not qualified. He says, no, you're not. But if I write to the admissions tutor at Portsmouth Poly and I say, look, I think this guy's got a chance, he'll probably let you in. So, Mr. Seth, wherever you are now, thank you very much. I mean, that was a real turning point. So I went into the first degree in mechanical engineering. I left. As Hamid said, I spent some years as a designer. If you've ever had an X-ray taken inside your mouth, they put the X-ray up here, and you're gripping the film. I used to design and prototype the machines that used to process those films. Not digital. This was long before digital photography had anything like the right resolution. But then I got made redundant again. It was becoming a habit. And so I went and did an MSc at Imperial. And then everything really changed. So these were the books that really influenced me when I was there. These are the people. I'm going to put a lot of names up. I've tried to remember a lot of the people that have influenced and been important to me over the years. So this was Imperial College, and I really took, with the help of John Barrett, sadly no longer with us, but I really took some finite elements. And the connection, I didn't realize this, but the connection to Brunel had already been made. Because if you look at that book here, the silver one, and zoom in on it, G.D. Smith, Brunel University, senior lecturer. So I hadn't even known this. I hadn't even known I had a Brunel connection when I was doing this MSc. But I saw this advert, PhD studentship, fully funded by SERC. John posted it in the newspaper, in the Times Higher. So I applied, and I went, and he accepted me, and I came to Brunel. I wanted to be an engineering consultant, so the idea was I get a PhD, then I'll leave. But I've really been wheel spinning ever since, and I got involved in this whole finite element. One of our colleagues called it a mecca once. All these MATHLAB conferences we got involved in. John had been doing them since the 70s. They went on and on and on. They only stopped because of COVID, and we're looking at resurrecting them now. So what was it all about then? So this is the the first part of the subtitle, decay. So enough about me. This is sort of what I do at Brunel and what I've done, and I guess the reason for being asked to give this lecture. So this was the topic that John had put, the proposal that John had put to SERC. He's probably long ago forgotten about this, but this was the project that got funded, and this was the equation. I spent 3 years getting a PhD studying that and equations like it. These are viscoelasticity problems. We wrote loads of papers. Mike was involved in a lot of these things as well, and really productive, enjoyable time. So now we come to this problem with equations. So I'm thinking, what am I going to do? How am I going to do a talk like this if I'm not, if it's a public lecture? And I was reminded of this apocryphal, or maybe it's true story about Stephen Hawking. So I had to make a decision. What will I do about equations? And I thought, well, actually, at this point in the talk, everybody's going to be sitting quietly and settled. So I could arrange for the door to be locked and do that. And I thought what we'd do is we'd spend half an hour on each equation. No, I'm only kidding. But I will do this. I'll put this one up. So this is viscoelasticity. Julia had this up earlier on this morning. He had it more complicated. There are two springs here, and this thing is a dashpot. The springs are indicating elasticity. The dashpot is indicating fluid viscosity. Julia works with things where the dashpot is a fractional object. So the decay, I think. So these models can be arbitrarily complicated. I keep the simplest one up. The point about these is that they have a constitutive law that relates stress and strain using integral calculus. And when you put that into Newton's second law of motion here, you get a partial differential equation that you can't solve, at least not by hand. So you need to solve it using computation, and that's finite elements. So that's the maths. Well, what is it? What is a viscoelastic material? It's somewhere between a solid and a fluid. So let's look down here and I think about silly putty. So in a minute, an orange blob's going to appear there. Keep your eyes on it because it will move, and then it will move again. Okay, the first movement is the elastic movement. Right, watch. There, it moved. Now it's going to flow. And then watch the watch. Okay, it's a very slow moving flow. So the elastic bit is a very fast elastic response. Thereafter, it's a very slow moving viscous effect. It'll go on forever. If I left it for a month, it would all end up as a puddle in the lid, but we won't wait for that to happen. So, for those electrical engineers in the audience, anybody interested in Maxwell's equations? It turns out that these mathematical formalism, these integral relationships, can be used in study of dielectrics as well. So this is a great thing about maths, is that once you write something down, you end up seeing that actually that same formalism can be applied all over the place. So Debye dielectrics have essentially the same structure as viscoelasticity. So this is unfinished business for me. COVID got in the way, so I lost contact with these guys, but I hope I'll pick it up again one day. So loads of work, and I really do have to hats off to John here, because he really worked hard and he funded me as a postdoc when times were quite difficult, and we just kept plugging away at it. And I think, there's a lot of people involved in a lot of different papers that have been written. Mary Wheeler in particular and Clint Dawson, that was massively helpful. Afternoon they spent here, taught me stuff that I would have taken me months if I'd done it on my own. Beatrice Riviere, we pulled that forward even more. I went to the EPSRC summer school. Steve knows about these things. We don't have them anymore, but I met Klaus Johnson. He was essentially reinventing finite element analysis and a posteriori error estimates. And that gave me what I needed to have a career, because I realized that whole approach could be used in viscoelasticity. Then we picked up with Arthur Johnson and Alex Tesla. Alex might even be online. Hello, Alex, if you are. They were at the NASA Langley Research Center. Alex is NASA, Art was US Army. And this was an established connection that John had. We picked that up to study adaptivity in viscoelasticity. Two major projects, EPSRC funding, and then we went to the US Army Damping Conference and met a guy called Tom Banks. Now I'm going to come back to Tom later on because he ended up being a really important character. So we were doing adaptivity. This is the US Army. This is what they were interested in. They wanted us basically to do adaptivity with viscoelastic materials and see if there was any potential in it for them. So what is adaptivity? Well, it's a computer simulation. So what we're doing is we're using computer methods to solve partial differential equations. It's a computer simulation that is able to automatically spend effort and resources where they are needed. These days in AI and data science, we call this unsupervised learning, but it's just where an algorithm learns from itself. So the algorithm can adjust its performance and behavior according to the data it generates. So at this point, I thought, maybe I'd do a demonstration. So I need a volunteer. Who wants to volunteer to help me do a demonstration? George, you're going to volunteer? Come on then. This is my grandson, everybody. You're a star. What I'd like you to do is, where's that metal bar gone? I have a metal bar, never mind. What I want you to do, if you can, is to come over here with me, and I want you to hold that high and really, really tight, okay? Don't let go of it. Oh, sorry. Oh, that was my fault. I did it the wrong way around. There we go. Okay, now hold it. Hold it really, really tight. Now, what I'm going to do, hold it up high for me, George, please. Right, hold on tight. So I'm going to bunch the spring up like that, and I'm going to let it go. Now, I mean, most people know what's going to happen, right? But indulge me. Right, ready? Hold tight. Okay, see that? There's a pulse moving. Okay, brilliant. Thank you, George. Let me tell you why that's relevant. Thank you, George, very much. So, in case you didn't see it, and for those people online, this is the spring, and this is what's happening. So there's a pulse, and anybody who knows about this stuff knows that this is the D'Alembert solution to the wave equation. Tell I don't do this very often, right? I've got my microphone off. And in reality, this wouldn't happen because it would damp out. So I just put this on. Watch it in slow motion, right? Look at that pulse. If you wanted to simulate this computationally, and you wouldn't because you can solve this exactly, but it's a demonstration. But if you wanted to simulate this computationally, you'd only want to put any effort in where things are happening. And where things are happening is moving in time. But the rest of it over here, nothing's happening. So you wouldn't want to spend any resources on that. So what do we do? So we started to work with space-time finite elements. Can you hear me? Because I'm concerned this isn't working. Oh, yeah. We started to work with space-time finite elements. Now, most people who work with finite elements are really familiar with the fact that you create a mesh and you discretize in space. But the idea here is that you discretize space-time. So here you would have your space direction, which could be multidimensional. Here you have your time direction. You break space-time up into little squares or little elements, and you approximate the unknown function with simple things like planes, bilinears in this case. So let me say I wanted to simulate the spring. This is x, this is space. So this is one end where George was, this is where I was, and the spring, the pulse is going forward and backward. Time is going that way. So actually, things are moving like that. So in an adaptive algorithm, you'd set a mesh up, and then you would use the information about the solution, something called the residual in this case, to inform how to refine that mesh in order to capture the behavior better. And this is what happens. So this is like an unsupervised learning algorithm in modern parlance. The algorithm is doing it all on its own. We're just giving it the method that it needs, the formulae that it needs. And then when it reaches a certain tolerance, it's done. And if you zoom in on that, you can see that it's selected certain elements to be refined and left other ones alone. So this is what we were doing, and we spent a lot of time doing this. And then something happened that diverted the US Army's interest in another direction, and we had to move on. Right? It came to an end, as most things do. So that was one part of the title, decay. The other part of the title, dead poets. So at this point, I still thought I'm going to be an engineering consultant. Research was great, but I was also teaching. And teaching and research are great, right? So there are three strands to this job, and two of them are just great. The other one, we have to do it, okay? So when I came, I started teaching very, very first day I got here, pretty much. I just said I want to do some teaching. And I did it by the book. But then something hit me, and it really came down to this guy, Robin Williams. So I went and saw this film. I don't know if you've seen this. If you haven't, I really recommend it. So basically, it's about Robin Williams being Robin Williams. and being a teacher and really holding the class. Not by just going through the motions and teaching and imparting knowledge, but essentially by turning it into theatre, just running a show, improvising, making up as he goes along. And for me, that was completely liberating because I thought I could do whatever I like in this class. Of course, I've got to be responsible, but it's up to me. It's up to me to engage the students in whatever way I can. So I thought, this is it. This is what I want to do forever. And with the support of, I mean, it was John, absolutely, Gautam, Ken Darby Dowman. I stayed at Brunel. They fixed me up. I became employed as an academic. Highly unlikely one at that point. I couldn't believe myself. Couldn't believe my luck. Now, I am always interested in research. That is the reason I do this job. But if you don't like the teaching, it's hard work because there's a lot of teaching and you've got to enjoy it. Otherwise, the days are just long and boring. So, you know, this for me, if you have seen the film, you know what I mean here. I Captain My Captain. Right? That was Robin Williams' address in the film. So I use this sometimes with the students because they will call me sir. Excuse me, sir. And I say, don't call me sir. It's not the military. You know, we're all adults here. And then 5 minutes later, excuse me, sir. So Robin Williams said, if you want to talk to me, if you want to refer to me, you say, oh, Captain, my Captain. Heart disease, the third part of the subtitle. What's that got to do with maths? Well, I guess because they make you ill, all of those things. And one of the ways in which they make you ill is by blocking your arteries. So you can get blockages in your arteries, these plaques or lipid deposits. There's a real one up there. Here's an artist's impression of one. We're talking about these arteries running down the outside of the heart here. I don't know all their names. They're left aortic, descending, and all kinds of stuff. I don't know all their names. 180 people die each day of some sort of cardiovascular disease. It's the third biggest killer. If you factor COVID out as an anomaly, it's the second biggest killer. 260 cardiovascular hospital admissions every day. Annual cost, I think it's about £9 billion direct cost, or something like £19 billion cost of the economy. It's a really big deal. This is your slide, Steve. Thank you very much. You don't know I took this because I forgot to ask you, but okay. So what has this got to do with maths? This is all thanks to Steve. I'm going to use his slide here. What happens is the blockage in the artery, or stenosis, or an occlusion in the artery, causes disturbed flow. So this disturbance comes downstream of the flow comes downstream of the disturbance, starts whirring around, and is causing vibrational noises on the artery wall. Those vibrations generate shear or pressure waves, stresses essentially, that are traveling at acoustic frequencies to the, I'm sorry, you can't read it. It says soft tissue and skin. So these things, these vibrations travel to the chest surface. And now, if you can then imagine that you put sensors on the chest surface, you can hear heart disease. Okay, that's the idea. It's very, very faint signals, but they are there. So this has been done with the carotid, which is quite, I won't say easy, but it's right there. You can almost look at it. Whereas we're thinking about heart disease, which is buried underneath the rib cage and nestled in between the lungs. This simulation actually was generated by Viviana, who was a PhD student of a guy called Patrick in Belgium. So we're not doing CFD, but please understand that. This is an enormously challenging problem, and if we want a device that will diagnose heart disease, we can't afford to solve the Navier-Stokes equations. So this is just simply an illustration. So what we're going to try and do then is use these partial differential Volterra equations. So this is viscoelasticity because the skin and the biotissue is viscoelastic. And we're going to try and use these equations to model this process and to come up with some sort of an inverse solver so that If we know what the surface signal is on the chest, we can diagnose the presence or the nature of the heart disease. I won't go into all the details. This came from years back. Now, this is where Tom Banks really played the important role. So I mentioned him earlier on. We met him at the Damping Conference. He told us about this. He was involved in it in the States. It was funded by venture capital. That venture capital dried up. I think it was the e-commerce boom, and the project went dead. Tom was an extremely garrulous and energetic guy, and he didn't want it to die. So he came over to us and he said, look, we need to get this up and running. So we said, okay, we're in. We could do the computation. He could do the inverse problem, but we didn't have anybody doing experiments. Serendipity struck. John had dinner with Colin Berry, mentioned it to him. Colin said, you need to talk to my PhD student. Was it a postdoc or PhD student? Even later, yeah. My colleague, you need to talk to Steve Greenwood, who's sitting here, because he can do your experiments. So we all teamed up and we got some funding. And after many, many years, didn't get the funding the first time round, I don't think, we finally got something that worked. It was very, very raw and very crude, but essentially we could solve an inverse problem so that after 20 or so iterations, we could localize the position of a disturbance in an in vitro, highly simplified geometry. Right, long journey. But it was never going to work, not in practice. It was way too slow and clumsy and clunky, and this was way too simple to ever be deployable. So we stalled on the methodology and the funding here for quite some time. A lot of input from Marie Johnson, who launched a company in the States doing something similar, but with signal processing methods, I believe. It was a little bit secret. We tried some filtering attempts with Paris Date. Ashraf was involved. Some of you know Ashraf. He's moved to Dundee now. But we couldn't really find the way to do this, the way to go forward. And then machine learning and the whole data science and AI thing took off. And it was kind of obvious to me that this is a machine learning problem. If we could generate the data, we could train a machine learning algorithm to do the diagnosis or even the screening, just the screening. So here we are, from machine tools to machine learning. So that's the title, that's the journey. So what did we do? Well, it's all virtual at the moment. We took a rectangular domain in 2 dimensions. This simulates the kind of setup Steve has in his lab. We choose a point at random, and we create a disturbance at that point. And then those 5 little dots along the top are where we pretend there are sensors. We pick up readings, strains, stresses, whatever we choose to. And we feed this through a neural network. It was actually a recurrent neural network, and this was done by a colleague of ours in Mask, Martin Barberis, who's now left. So we were at a point where we were starting to collaborate and starting to build something, but he decided that he wanted to go elsewhere, and he left academia. So basically, this whole thing stopped, and let's restart it. And I couldn't really do it on my own very quickly. It was, it was useful when 2 of us were doing it. But by and large, this is what happened. We, if you know about this stuff, we generated a whole bunch of training data. That's at the top. And then the red crosses were the attempts to identify the position of the blue dots. That's the training data at the top. The test data is down here, which is what matters. And you see these red crosses around here trying to locate that blue dot. So it's not a very good approximation until you average the red crosses. And then you get this. And then you see each of the red crosses are quite close to the dot. So this was our proof of concept. It works, right? We can do this. And at least the simplest setting, we could do this. Again, it's sort of time-consuming to do if you don't have a good supply of PhD students and postdocs, which we didn't at the time. Luckily, Steve bumped into a guy called Greg Slabow. Greg runs an MSc course at Queen Mary and said, I've got loads of MSc students who are looking for data science projects. So we talked to Bansi. She wanted to do a project. We gave her loads of data. What we do is we generate loads of random sources here. We generate the signals. And she tried out not just neural networks, but a whole bunch of machine learning algorithms. And we saw that in a large number of cases, this works. Okay, so it's now the basis of a really useful and rapid, once trained, rapid way of deploying this methodology. And why is it important? Well, it's not that there haven't been attempts, but at the moment, a cheap and easily deployed, democratized, by that I mean available to everybody, non-invasive diagnostic screening tool is not available. What we're thinking about here is just picking up signals on the chest surface. Most of us wear Fitbits or something these days. So it's not unusual, is it? It's not unusual to just have something sitting on the skin that's telling you about your body. And that's what's going on here. That's what that aim is. So devising and implementing the necessary algorithmic features, the software of such a device is a major effort involving us, Queen Mary, and Neelicast Limited. So here we are. Steve just went and picked up the latest version of the sensors today. I think they've been built. That's the things on the left. The early version was up there. That's a picture of that rectangular slab from Steve's lab. These are the data that I just plotted these in Python just so you can see what it looks like. These are the kind of signals that are coming out. Raw data from several different sensors. What we've got to do is find now the right machine learning approaches to diagnose the source of the signal, to screen for it. It's all happening for real. It's not just academic research now. Neelicast Limited was spun out on the 8th of February 2023. Mark is the CEO, and he's sitting here right now. So this is real impact. This is stuff that is really, I hope, going to make a difference. So I used to love proving theorems and getting error estimates, and I still do, but I kind of think now I want to do stuff like this because it's better, right? It's better for us all if maths can do stuff. But it's not the only thing I'm interested in. It's not the only activity I'm interested in where we're putting maths to work. RSDO ran a knowledge transfer and secondment research leave scheme. And so with RSDO, with Teresa and the team's help, and with Matthias Maischak, sorry, I just remembered I've got some water. Excuse me a minute. Right. And with the support of Matthias Maischak, who was head of department at the time, I was able to spend 40% of my time on a knowledge transfer and secondment leave. How did it come about? Well, I went for a crazy day out at Sandhurst with the reservists. Don't ask me how. And I was absolutely wiped out. I was in no state to do this. But at lunchtime, we were sitting in the woods, eating curry. I didn't have a seat with the group I was sitting with, so I went and sat with this complete stranger. And we did what any two complete strangers eating curry in the woods would do and started talking about quantum computers. Turned out that was Matthew Martin, who was, I think, Director of Engineering at Oxford Instruments Nanoscience. And he said, look, we're really looking to expand our university outreach. Why don't you come up and talk to us? So Jeff, I don't think he's here, Jeff Rogers and I went up one Friday morning. Tassos got involved in this for a while as well. But we had to sort of pick one thing to go forward with, I think. And we met Andy Twin, who's sitting over there, Andrew Varney, who said if he could find a place where he could have a pint and dial in, he might be online as well. Roman Zuchenko, and lately Arkady as well. And what we did, really, Roman and I sat down and did what Matthew called code archaeology. And we went through thousands of lines of old Fortran simulation code. The code was used to simulate superconducting magnet quench. Off the back of that, we got an EPSRC doctoral mobility pilot. So Oxford Instruments released Stephen Ball, who's sitting over there, to do a PhD with me, part-time PhD, where we're looking to develop a novel finite element method for quench. I'm not going to tell you about it because it might have commercial value, and seriously, we might have to think a little bit hard about how we deal with that. A little plug for maths, though. This was a few thousand quid, and it came a long way, right? I mean, it's a real embedded relationship now with Oxford Instruments. And it's sometimes maths gets a little bit lost in the college we're in. I'm not criticizing it at all, but maths isn't really like the other departments. We don't need lots of labs. We just need a few thousand quid every now and then and a little bit of headspace. And we can leverage that hugely. And it sometimes gets a little bit lost in all the policy making that goes on. So just wanted to put it up there because hopefully that's going out on YouTube. Somebody might tweet it. Let me just tell you about Oxford Instruments. So they're leveraging superconductivity, discovered in the early part of last century, made commercial in the 60s. Andy and Stephen could tell you all about this later on over a glass of wine if you like. But we don't realize it probably, but this is getting used a lot. And it's very green because superconducting materials don't have any resistance. So they're transferring energy at very high efficiencies. So it's a very good thing to be doing in this world of ours. What is quench? I'll tell you very briefly, very quickly. If a material is a piece of wire, right? Superconducting material, it's a very low temperature. If for some reason, maybe there's a manufacturing defect, that area goes normal, what that means is it stops superconducting and goes back to being resistive. What will happen is an enormous amount of heat will get generated. And that heat will travel really quickly. And loads of bad stuff happens then. People could get hurt, equipment can be damaged, profit margins can be hit. So it's important to control this quench and to shut the machine off very quickly. Now, I've probably oversimplified that in such a terribly vulgar way, but that's basically the nature of the problem. So can we simulate it? Yes. It's basically a heat transfer problem with some nonlinearity, and that's really the basis of Stephen's project, but the rest of it's secret. I'm not going to tell you how we're going to do it. So that's it then. I've just explained my title. Started with machine tools, machining things to maybe a thousandth of an inch. And now, heart disease, picking up chest surface signals, which again are around about a couple of thousandths of an inch. So I kind of started with small lengths and ended up with small lengths. So I had a circularity to it. I hope you now understand why I gave it such a strange title. And I hope there weren't too many equations. What next? Well, I'm going to carry on doing all of the things that I do, but this picture keeps coming back to my mind. I saw this a long time ago. And when I was writing this, you saw the amount of names I put up. And I was struck by how many times I wrote RIP. And it kind of made me think a little bit, and I started to color this in, think about where I am with it. And it's been a hell of a journey. I mean, I really enjoyed it. It's been great. But like I said earlier, I've enjoyed what I did. I want the next bit to be different. And I think the heart disease, the superconductivity, and the quench is the way in which it's going to be different. One thing that I wasn't going to say this, but I was talking with Hamid earlier on. When you look at that, I mean, no, I'm reasonably well educated, right? I had a lot of breaks. I didn't pay for any of this stuff. And think about what everybody's going through today, how much it costs just to get a degree. I got grants for all of this. But think about the world we have now. I mean, it's a really complicated world, isn't it? All this AI and data science, all these ethical problems, complete instability, information traveling faster than you can believe. And yet we still have the same educational model. We don't spend much time educating people, really. I mean, it's almost like this lifelong learning that we talk about. It's almost a civic duty, I think. Of course, we're never going to get to that, are we? Because we're going to reintroduce national service instead. But let's not get political. So I don't know really what comes next. None of us do. That was what writing all those RIPs made me think. So I think, I think it's important to think about what you're doing and where you're putting your energy. So I don't know if it's appropriate to give advice here, but if I was to give advice to people, I'd say, know where you're going to put your energy. Peter Thomas, when he did an inaugural talk a little while ago, introduced us to the word rusticate. He said nobody uses it enough. It means to go and live in the country and let other people do the hard work. So my word for you is defenestrate. Learn to defenestrate. Defenestrate means throw it out the window, right? If you get a task that comes at you and you think, hang on, that's got no value to it, defenestrate it. Throw it out the window. Get rid of it. For me, though, I'm moving into this machine learning and AI field with the Neelicast project, and it's making me think about data science and data. I lived in a closeted and comfortable world of mathematical certainty and axioms. Never had to worry about the real world, and then it gets to data. Of course, data is a real, dirty, ugly thing. And so I thought I'd leave you with a little illustration of that. And this is thanks to Dan Warren, who was a PhD student with us, even an undergraduate, I think. Now works with Triple E on their industrial advisory board. So if you indulge me then. If you consider yourself to be a bit of an introvert, you just kind of like to sit quietly, not really get noticed, not, just keep yourself to yourself. Could you please raise your left hand? Okay, great. Now, if you consider yourself to be a bit of a maverick, a rebel, you're not going to tell me what to do, right? I'm going to do it my own way. I'm not following your lead. If you consider yourself to be like that, could you raise your right hand? Okay, great. So we've just collected some data. So let's ask ourselves then, where are the introverts? And where are the rebels? Well, I would say the introverts are not in the green circle, because all of those people who don't like to be noticed in a crowd, when I said, put your hand up, and I would say the rebels are not in the red circle, because all those people that don't do what they're told, when I said, put your hand up. So it's a bit of fun, of course, but I don't know where it came from. Dan couldn't remember where it came from. But it's just a nice illustration that once you step out of lovely axiomatic world of maths into the real world of data, suddenly it's messy and it's noisy and it's difficult and you have to think hard about what it is you're doing. So I hope I'm on time. I hope I haven't kept you too long. Always, of course, thanks. I put up a lot of names. I'm sure there are people I should have put up and I didn't. So there's a catch-all thanks there to everybody, everywhere. There's so many people that we lean on, aren't there? We're in all walks of life, really. But it's easy to think, oh, it's another day and I've got to do all this stuff. But there's loads of people in the background all the time, and there always have been. So thanks to all of them. Unusually, I'm going to thank the whole of the GNU Linux and open source movements, because without that, I'd have done nothing. Seriously, nothing. Because everything I do is done in Linux. Everything meaningful. My typing is done in LaTeX. My coding is done in Python. It's all free, open source. It all comes through this sort of non-Apple, non-Microsoft channel. And if it wasn't for that, it's not just me. There's whole swathes of computational mathematics that just wouldn't really exist. Earlier on, I put up some names. One particular name I put in red. That was Carolyn Sellers. So Carolyn Sellers was John's PA, came along and worked for him, and we worked together a lot doing MathLab. And then in 2011, Carolyn Sellers became Carolyn Shaw. So we got married. And the biggest shout out tonight is to these guys here and the ones who aren't here because they're putting little ones to bed. Thanks to the ones that are with me in my heart and my mind all the time. Thank you, everybody. Thanks for listening.
Thank you very much, Simon, for your fascinating and inspiring lecture.
You're welcome.
And now we have some time for questions. So open to the audience now. If you have any questions, please.
By now, you'll have heard an awful lot about me, John White. I was director of Bicom for 40 years of its existence. During that time, I was a student. And I was suddenly aware that the student and the PA were getting very friendly. Now, the trouble when you're time diagram up the 90 corner, when you're near there, people treat you as blind, deaf, dumb, totally jealous. And there was me thinking, oh, get on with it. And Karen came to me one day and she said, Simon and I are going to get engaged. Thank goodness for that. And I consider one of the major achievements of Bicom in its 40 years was to bring those people together.
Thank you very much. Good job.
Well, that was a comment, not a question. So if you have any questions, please.
Simon, with your slightly different way of coming into academia, do you think it causes you to look at things slightly differently in comparison to your other, perhaps, A-level initial degree colleagues?
I think so, but I actually yeah, I think so. I think that's true because I have a different background, and so I think I see students in a different way. I understand probably, not saying that other people don't, but I've got complete sympathy with the idea of widening participation and the idea that, you know, everybody kind of deserves a break and everybody deserves a chance. But, you know, I don't know if I'm that different really. I think I was saying to Tassos the other day, he said, oh, you've got an interesting write-up. And I said, well, I used to think I was different. But then when I started meeting other colleagues and talking to them, we're all different. You know, we're all come from such a wide variety of backgrounds. A lot of people not you know, educated in different countries, different types of institution. So yeah, I think it does give me a different way of looking at it, but looking at things. But I think everybody probably has their own spin as well. So it's a bit of both, maybe.
Any other questions? Yes.
Yeah, I've just got a simple question. You said it doesn't cost much to do what you do, but do you need fancy, expensive computers?
Oh, good question. So it's nice if you do have fancy, expensive computers, but often no. And when you get to the point where you do, you can apply for time on the National Computing Service and so on, and you can maybe even get you know, hitch a ride on a departmental machine, or sorry, a college machine or something like that. So no, a lot of the time no. Some of the more theoretical colleagues, they don't really need much other than a laptop and maybe a few software licenses.
So the machines, those bits of metal that you showed at the beginning were really impressive. One of them was a sort of slab of metal, a bit rusty.
Yeah, they're a bit old now.
What was it?
What was it? Let's go back. Let's see if I can find it.
Sorry, I didn't mean to make you.
No, it's okay. Oh, sorry. Again. There you go.
Yeah, so the top picture there, that's it. Yeah, it looks like a stage.
This one?
Just below it.
This one?
No, below it.
This? Oh yeah, actually, it's a little ashtray. So it was a copper burnished ashtray. So it was a triangular cut. It was burnished down on a tab. I can't remember what they call them now. A ball peen hammer and a little soldered ring underneath. So it was an ashtray. Yeah.
Much more impressive.
Lady at the back.
Hi, Joe.
So just wait for the octopus to arrive.
Yeah. So some of you might know that Paris Date and I took on a joint head of department role. And so I don't do it. So it's sort of denied to me now. But I think historically I've always done it by just staying at home. And I mean, this is before COVID even, just having a day at home and just taking stuff with me so that I knew that I had that thing to do and I'd hopefully get to the end of the day and it would be done. That was easily the most effective way of ring-fencing time for me. It sort of became normal during COVID to be at home, of course, and then it's become normal to spend lots of time at home now, and that's kind of destroyed that because now being at home is just like another working day. Brilliant. Yeah, Teams has been a really backward step. Means you just can't hide anymore.
If I may ask a question myself now, Simon, you've spent most of your career in physics-based modeling, and now over the recent times, you've kind of slightly diverted to what we call database modeling.
But yeah, data science.
Data science, yeah. There is currently this notion that data science modeling will eventually take over the requirement for physics-based modeling. I don't personally believe in that, but I just wondered what your view is on that, because I think at best it can probably optimize it, like the parameters that go into a physics-based modeling, but not necessarily replace it. I just wondered what your view
I
is.
don't completely agree. I think it's another tool. So people do think that large language models are going to take over the world. I don't really agree with. I don't think that's the case. I think that machine learning is, when you look at it, it's applied maths with a decent amount of statistics thrown in there and quite a lot of high-end computing. The libraries that require a lot, but it's applied maths and it's just yet another tool. So years ago, if you inverted a matrix using LU decomposition and it took half a day, and then somebody came along with a conjugate gradient method and it took an hour, well, what we have now is a new kind of tool, which if you invest in the training, you could probably solve a PDE in 5 minutes. But yeah, I've got to put the time and effort into doing it. So for me, it's another tool. I don't think it's going to be Arnold Schwarzenegger anytime soon. I don't think there are Terminators coming over the horizon, and I'm not even that worried about student work, not in maths, because I still think it's quite easy to spot this stuff. Now, I don't know if that's still going to be the case in 2 years' time, because they're getting better. I mean, if you ask something to, have you noticed that suddenly there's a glut of emails and the first line is, "I hope this email finds you well." I think that's ChatGPT. Because I mean, that's an old phrase that I haven't heard for years and years and years. Now suddenly everybody's using it. So there's a lot of telltale signs for this stuff. I don't know if it'll stay that way, and I think maybe we've got a bit of a problem with assessing and that sort of robustness. But as far as computational maths is concerned, I see it as another tool, and I see it as a really, really important and useful one. I mean, this problem we're trying to solve, we had nowhere to go with it. But it does look to me like machine learning is going to turn. I think we'll create a device that will be able to screen for heart disease in the same way that this can take an ECG. So, yeah, I don't think it's going to replace anything. I think it's just going to make all the things we've got better.
Thank you. Any other questions?
A 30-second comment first, Simon, if I may. At the plenary lecture in Florence, the speaker said, if you travel for more than 100 miles and you carry slides, in those days we used to go without slides, then you must be an expert. I thought he was wrong, actually, because I think coming from your office here to give this lecture is more of being an expert than actually going somewhere else. So I think this is a very important lecture, and I thank you very much for an excellent.
Thank you, Tassos.
My question relates to Hamid's, actually. We go from mathematics and engineering, which is a precise science, or as much as possible precise, especially in mathematics, to CFD modeling, and then now machine learning. Are we learning to live with uncertainties as we move on into the future, or is there do we need to re-educate ourselves, including industry?
That's a good question, isn't it? So I think that some problems, I think you have every right to expect certainty. but there are lots of other problems where it's kind of just beyond reach. You can't do it. So if we wanted to detect this heart disease, what we're dealing with is not a whole population of people who are exactly the same. Every single person is slightly different. So whatever we do, however we optimize and however we tune, there's always going to be error bars. There's always going to be, the fact that somebody's a little bit of a different shape. I mean, half the population is a rather different shape, right? So there's loads of uncertainty sitting around there. I think even material properties. If I said to you, what's the Young's modulus of that specimen you're testing? And you say to me, so it's like that old joke, right? You remember you may have heard this. So there's the guide in a natural history museum is taking a group of people around, and they get to a dinosaur skeleton, and he says this skeleton is 19,021 years old. And somebody says, how do you know it to be that precise? He says, well, because 21 years ago when I came here, they So your Young's modulus for your material is going to be, you feed it into your linear elasticity model. It's not really linear elastic, is it? Your Young's modulus isn't perfect, is it? Your density is not perfect if you're doing time domain stuff. And then you're simulating it with an explicit abacus, which has got tons of discretization error anyway that you're desperately trying to control. So I think we've always had uncertainty. I mean, what Julio's trying to model materials are incredibly uncertain with an exponent new. Well, he's going to capture it, but it's not going to fit that curve exactly, and he doesn't want it to because he's going to spend his whole life getting it to wiggle around properly. But in the end, we want 10% accuracy, don't we? We want to make sure things don't fall out of the sky. So, yeah, I think that we've always had uncertainty, and I think what's happening with AI and data science and machine learning is that it's raising the profile of these statistical tools. And yeah, I hope that people will embrace them more because it's more work for mathematicians.
Great.
We always work on the basis that plus minus 2%. So that's the probability. That's what's
That's good, right? 2% is good. Yeah.
Okay. If no more questions, then I bring the session to a close. And thank you again, once again.
Thank you, Amir. Thank you, everybody. Thank you.